There's basically two types of inference in statistics. It's either doing a hypothesis test or building and constructing a confidence interval. Suppose a large company wants to estimate the mean average daily commute time for its professionals. If we were doing a hypothesis, someone would be making a claim like the mean commute time is greater than 100. That would lead to a null hypothesis that in essence said that the mean was equal to 100. So we'd use a normal distribution and a sampling distribution, and we would assume that 100 is the mean. Whereas if we're doing a confidence interval, nobody's making an assumption about the mean. So we're just going to say, well, we're going to a confidence interval. We know where the true mean exists, but we don't know where it is. And so we're going to use our sample result and build a confidence interval based on it. But the big difference is, in a hypothesis test, somebody makes a claim about a number, that number becomes the mean. Confidence interval, the unknown mean, goes in the middle of the distribution. So both distributions are sampling distributions of means. So theoretically, this is infinitely many sample means and how they're distributed. And if somebody made a claim like they did before, we would put 100 minutes here as the assumed mean of the distribution. And then we would test that idea by saying, let's go take one sample, and would that one sample result behave like it should if the mean is 100, or is it behaving like it's not 100 as the mean? Whereas over here in a sampling distribution, there's no assumption that's being made about the population mean. But it's very important that we understand that whatever the true population mean is, it goes in the middle. And we're going to use this understanding of a sampling distribution with an unknown mean in the middle of it as its center to build this idea. Now it starts with the basic idea. It kind of starts with the empirical rule. In particular, let's go to this guy right here. Do we agree that if we went over 2 standard deviations in each direction, we would tend to trap the middle 95% of all of our sample means? That leaves 2.5% to the right. So if we do this, if we go over one, it actually turns out to be 1.96 standard deviations. We got that from the other day. We looked at critical z-scores. That's actually the number of standard deviations you travel in each direction to trap the middle 95%. Okay, so keeping that in mind, here's the deal. Mu is the true mean commute time. Now suppose we get an X bar that's 108.2 minutes. The nerd might ask us, where is mu? But if we really want to understand the confidence interval, the better question to ask is, where is our X bar in relation to mu? You see, the true sampling distribution has this unknown mean in the middle of it. We know that. What we want to know is, whenever we take one sample mean, where should it lie in relation to the true mu? So where is X bar? Well, if we go back up here and we say, you know what? In 95% of all samples, you would expect your sample mean to be within that many standard deviations of the true mean. So where is X bar? It's probably less than 1.96 standard deviations, either above the true mean or below the true mean. So how does that help us build our confidence interval? Well, we know that this X bar of ours is probably within 1.96 standard deviations of the true mean. Guys, we're going to call this the margin of error, that we're probably within 1.96 standard deviations of the true mean. So what we do is, okay, let's suppose our sample mean is up here. Again, less than 1.96 standard deviations above the true mean. Well, if we take this margin of error and we add it and we subtract it from that mean, then there's a 95% chance that we're going to trap the true mean in that interval. And we're going to want to use the phrasing, then we're 95% confident that the true mean is within this margin of error of our sample mean. In other words, this true mean is within 1.96 standard deviations of our sample mean. How do we know that? Because this is the important question. We're pretty confident that this sample mean is within 1.96 standard deviations of the true mean, because that's the theory behind a sampling distribution. So one more time, if we say, okay, that's the margin of error right there, we go over 1.96 standard deviations in each direction, Well, where might our sample mean of 108.2 be? It could be above the true mean, but do you agree it could also be somewhere below the true mean? And if it is, if we say, okay, that's our value, then the true mean, it should be within one margin of error of that sample mean. It should be within 1.96 standard deviations of that true mean. That is the theory behind confidence intervals. Don't try to put the sample mean here. Too many kids say, oh, I understand the confidence interval. I'll put my sample mean here and I'll go over 1.96 standard deviations in each direction. That is not what is happening. This is what's happening. Where is our X bar? It is probably somewhere within 1.96 standard deviations from each side of the mean. So our sample mean is somewhere in this neighborhood in here 95% of the time. Every now and then we get a real extreme result. But our sample mean should be somewhere in here. That is why if we start with the sample mean and we add a margin of error and subtract a margin of error, we're 95% confident we're going to trap the true mean in that interval. So, suppose we took a sample of 36, we got a standard deviation of 42 minutes, and that's our sample mean right there. This is the formula we will use in AP statistics. We will take our statistic, which in this case is a sample mean because we're trying to estimate the population parameter mu, so we use our statistic X bar, plus or minus our critical z-score that we use. Now we just looked at using a z-score of 1.96 because that would trap 95% in the middle, and then we'll multiply this by the standard deviation of the statistic, which the formula sheet tells us, and we should remember, would be sigma divided by radical n for how spread out the sample means would be. This is how spread out one commuter's time, daily time is, one person at a time. But divide this by radical 36 in our case, and that would give you the standard deviation for this particular sample mean. So taking these numbers forward, what we would get is our statistic, which was 108.2 minutes, plus or minus the z-score of 1.96. We should know that 95% of the time we should be within 1.96 standard deviations. This gets multiplied by the standard deviation, which was the 42 minutes, but we're going to divide that by the radical of the sample size, the square root of that, so this would be 7. So we would get 108.2 plus or minus 1.96 times 7 minutes. Now we could just estimate this. In the next video we're actually going to finish the process and we're going to formalize it. But check this out. This is the margin of error. This guy right here. This is what we're saying, that if we have this sampling distribution, we don't know what the true mean is, that's what we're trying to estimate, but this margin of error, 1.96 of these standard deviations, that's about 2. 2 times 7 is about 14. Roughly, we'd be going over about 14 minutes in each direction. So there's a 95% chance that this particular sample mean, our one sample mean we got, should be within 14 minutes of the true mean. So no matter where this sample mean is, whether it's up here or down here, there's a 95% chance that this sample mean is somewhere within that margin of error, which is 1.96 standard deviations. So it must be true that if we take this guy and add and subtract this margin of error, we're going to get a confidence interval that should contain the true mean. So roughly speaking, that's 108 minutes. If we add 14 minutes, that takes us up to 122 minutes. And if we subtract 14 minutes from 108, that'll take us down to 94 minutes. So we'll learn to basically say that, you know what, we're 95% confident that the true mean commuting time of employees in this company is somewhere between 94 minutes a day and 122 minutes a day. So there you go. There's the idea behind a confidence interval. Now in the next part, we will formalize the write-up and how we go about doing it.